Okay, so if you look at the parallels, you should see that they are very similar. Charge is, the letter for charge is Q. I don't know why, but it's Q. So what this is saying is the electrostatic force, the force that happens between a positive charge and a negative charge, is FQ, okay? Because the charge itself is Q. So this is Q1 and Q2. This is the size of the charge, just like this is M1 and M2, the size of the mass. The R is the distance from the center of one to the center of the other, just like it is in gravity. And the K is known as the electrostatic constant. Okay? Electrostatic constant. And in physics, we use K to be 9 times 10 to the 9th Newton meters squared per Coulomb squared. We won't use it often in Science 12.2, but the couple times we do, we'll use it as the more exact number, which is really 9 point, I think it's 9.988. 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. A couple of times we use it to solve for another number that we need more exact. Okay? Look at its units. It's newtons per meter squared per Coulomb squared. This guy was newtons per meter squared per kilogram squared. The only thing that has changed is the coulombs, the charge. That coulombs is a measure of charge. And so the charge has replaced the kilograms. Both of these forms, both of these equations, take the form of what's known as the inverse square law. And what it means is that the force is inversely proportional to the square of something. And scientists get really excited when they find this form for an equation, because this form shows up naturally in all kinds of things in our world. Lots of things obey what's known as the inverse square law. So if you were working on something, trying to figure out how things are related, and you see this relationship, get excited, because it probably means you're right, because so many things in our world obeys what's known as the inverse square law. Okay, so this is the equation for electrostatic force. But really what I wanted to talk about were electrostatic fields. So just like an object that has mass, like the Earth or the Sun, has an area around itself where another object with mass, when it enters that area, experiences a gravitational force, an object around the area around a charged object also is an area where another object with a charge would experience a force. This time it'll be an electrostatic force. So this area around this charged object is known as an electric field. Okay, so now for gravity, the gravitational field we wrote as Gm over r squared up above. And this m is the mass of the object creating the field. We could also get this g by just doing Fg divided by m, right? Fg equals mg, Fg divided by m should give me the g. And this mass is the mass of the object being brought into the field. Object entering field. So it's going to be exactly the same for our electric field. The letter for our electric field is a capital E, and one way we can get it is by taking the FQ and dividing by Q. So it'll look just like this one, where this Q is the charge brought into the field. Yeah, how would we spell brought into field? And if you take your KQQ over r squared and divide by Q, you will also get another equation for field, KQ over r squared. And this is the charge creating the field. Okay, so they totally parallel the two equations for the acceleration due to gravity or the gravitational field strength. These are known as the electric field strength. Okay, charge is measured in coulombs, force is measured in newtons, so electric field is measured in newtons per coulomb. And it doesn't have another name, just newtons per coulomb. Okay, now oops, I need a new sheet of paper. The other thing we just need to talk about for a couple of minutes is what's known as electric field or field lines. Field lines are lines around an object that show the direction of the field. So if this is the Earth, the field lines really show the direction of the force that an object would experience if placed at that point in the field. So imagine this is the Earth, and I put an object here. What's the direction of the force? Downward. Here, inward, inward, inward. So the Earth would have gravitational field lines all around itself pointing in. There's a few rules about these field lines. Field lines are never allowed to cross. They're never allowed to cross because they're the direction that the force is going at that point. If they crossed, it would mean the force was going in two directions at once. Nothing can go in two directions at once. So that includes force. So they can't cross. But the closer the field lines are together, it indicates the stronger the field. So if you look here, the field lines are much closer than out here. It makes sense that the field is much stronger closer to the Earth. Electric field lines are the same. If you have a positive charge or you have a negative charge, they would still have field lines around them. Objects would experience a force. Objects with a charge would experience a force when they came near these objects. That force would get bigger or smaller, depending on how close or how far away you are. The only difference is that this time, the direction isn't a given. Gravity always acts inward, but electric fields don't. Okay? And so back a number of years ago, they defined the direction of an electric field by the direction of the force that would be exerted on a positive charge. So if I take this little positive charge and place it here, it's going to feel the force going away because opposites repel. So this guy is not going to like this little positive charge, and it's going to push it away. Whereas if I brought it near a negative charge, the negative charge would attract it. So we say field lines always go into a negative. Field lines around a negative charge are always going in. Around a positive charge, they're always coming out. Okay, so it's different from the Earth. It can be either positive or negative. If I bring two charges together, like two positives, and I look at what would happen to the field lines, they can't cross. So if I put a little positive charge here in the center, neither of them want it, and so the field lines do this. They try to push it away, but because they can't cross each other, they end up being curved. And I'm doing all this because as soon as we start magnetism next week, we will talk about magnetic field lines. They also can't cross. Okay, and so I want you to understand field lines so that it'll be easier when we get to magnetism. So the field around two positive charges brought close together would look like this. The field around two negative charges brought close together would look exactly the same, except the only thing that would be different would be that they would both want it, so all the arrowheads would be going in. Fields are vectors, so the arrows are showing the direction. Okay? And if I brought a positive and a negative together and put a little positive charge here, the positive one wouldn't want it, the negative one would. And so this time the lines help each other out. So the positive pushes